Welcome to probability video 10.9, conditional probability with medical screening tests. This example is pretty relevant to life in general. All right, so here's example 9. The American Diabetes Association estimates that about 9% of the US population has diabetes, and that is on the rise. A medical lab has a simple, inexpensive diagnostic test with diabetes with the following: a false positive rate of 3% and a false negative rate of 1%. So a false positive rate means you test positive, but you don't have a disease. A false negative means you test negative, but you actually do have the disease. Okay? So here's part A, so to draw a tree diagram. I'll do that over there. Then we got part C, B, and C, and D. All right, so part A, the tree diagram, I'll do that right here. So let's fill out the branches. Again, from each starting node, it should sum 1. So have diabetes, 9%. Let's make this be a decimal, 0.09. Not having diabetes, well, that would be 1 minus that, so that would be 0.91. Again, those two sum 1. Over here, let's fill out this. All right, so they said false positive of 3%. So that means you test positive, but you don't have the disease. So here, you don't have the disease, you test positive. So this is the false positive, and that would be 3%. Well, then this would be the true negative, and that would be 0.97. Again, they sum 1. False negative of 1%. Okay, so that means you test negative, but you do have it. You test negative, but you do have it. So this is the false negative, and that's 0.01. This would be the true positive. That would be 0.99. And these numbers are typical of what they could be. Okay, so that's part A. Part B, find the probability that a randomly chosen person who tests positive actually has diabetes. So as far as my general situation, somebody who tests positive. So let's find out where those branches are. Testing positive is this branch. Testing positive is that branch. So that's my general scenario. So remember, probability specific over probability general. So for my general, it would be 0.09 times 0.99, or this other branch, 0.91 times 0.03. My specific would be testing positive and actually having it. Testing positive and actually having it. So that would be this branch right here. So I'll just put a star, that's my specific. Okay, so that would be 0.09 times 0.99, and if you do the math, you get about 0.765. So that's a 76.5% chance of that. Okay, let's do part C. Find the probability that a randomly chosen person who tests negative really doesn't have diabetes. Okay, so I'll do some quick erasing here. So testing negative, I'll go red here. So here is a negative, and here is a negative. So those would be my generals. So for my generals, that would be 0.09 times 0.01 plus 0.91 times 0.97. And then my specific would be testing negative and not having it. Testing negative and not having it. So this would be my specific. Okay, so that would be 0.91 times 0.97. And if you do the math, you get about 0.999. So 99.9%. Okay, let's discuss. Discuss the advantages of using a screening system like this. All right, so here's how it works. if we've got to test the entire population, it's not reasonable to give everybody the expensive test and use up all those resources. So what we do is we can test a large part of the population using an inexpensive test. And then we can get results like this. And if it turns out that you test positive, it's not necessarily meaning that you actually have the disease. Then we could send you on for further evaluation, then give you the more expensive test. It's just a way of filtering out people that might not need the expensive test. Over here, let's say we give you the cheap test and it says, hey, you don't have diabetes. Well, look at this. It's almost guaranteed that you really don't have it. You would hate to have a cheap test that says, oh, you don't have this disease, when you really do. So you can have true confidence that that screening test, if it says you don't have it, you're good to go, for the most part. Okay? And just to let you know, the reason that works is when not a large part of the population has a disease, and when the negative rates, the false negatives, are a low number, look at what's happening here. We've got 0.09 times 0.01, that's close to 0, and something close to 0 added on to here, it's going to be close to this number. And whenever you get a number divided by close to itself, you get about 1. So that's really what's driving the mathematics behind that. So there you have it, how to use conditional probability with medical screening tests.